After you have prepared your data sufficiently, it's now time to create the machine learning model. As it has been for this entire series, my name is still Josiah. Just before we dive into the code, I'd like us to take some time to think about how machines actually learn. This is going to be our subject for this video. In order to do that, we shall be looking at the artificial neural network. This diagram here is an artificial neural network. We shall start by understanding how it works. Each of the circles in the diagram is called a neuron. The columns of neurons together make up what is called a layer, and we have two layers here. This leftmost layer is called the input layer, and the one on the far right is called the output layer. The job of the input layer is to accept inputs. And in this case, we're going to assume that we have two inputs, A and B. The job of the output layer is to give outputs. Layers that are adjacent to each other are connected via weights. And so we shall use weights of 0.4 for each of the connections. The weights do not have to be the same, but we chose to make them the same. We will learn how this structure works by thinking through a few examples. So let's assume that A and B, like we can see here, are binary inputs. So when A is 0 and B is 0, the job of the input neuron is simply to pass through the input. This input of 0 on the A branch is multiplied by the weight of 0.4, and the result that arrives here is 0. The same thing, 0 times 0.4, happens on the B branch, and the result that arrives there is 0. Once this result arrives at the output neuron, the first thing that is done is the two inputs are summed together. All the inputs are summed together, actually. If there were more than two, we would do that. And the sum of that is 0. Then this 0 is fed into this function f. Now this function, f of x, is such that its output is 1 when x is greater than or equal to 0.5, and it is 0 otherwise. Now in this case, x, which is 0 that's fed into the function, is equal to 0, so f of 0 is equal to 0. And so when a and b are both 0, our output y is 0. When a is 0 but b is 1, the same thing happens for the A branch. So the input A is fed through, we get a 0 there. That 0 is multiplied by 0.4, we get 0.4, and that is what arrives there. The B, on the other hand, what is passed through is the 1. That's multiplied by 0.4, and the result is 0.4. And the summation is 0.4 plus 0, which is 0.4. And f of 0.4, like we saw in our function here, is equal to 0. When we have a being equal to 1 and b equal to 0, then the input neuron passes through the 1, and we have a 1 here. 1 is multiplied by 0.4, and the result is equal to 1. On the B branch, we have 0 at this point, is multiplied by 0 and 0.4, sorry, and our result is equal to 0. You would see that 1 times 0.4 is actually equal to 0.4, and it's not equal to 1. Then 0.4 plus 0 is equal to 0.4, and then f of 0.4 is equal to 0 once again. Finally, when both A and B are 1, the A branch is not going to change because we already saw what happens when it is equal to 1. It's going to be equal to 0.4. In the B branch, we're going to have a 1 here multiplied by 0.4 gives us 0.4. 0.4 plus 0.4 is 0.8, and f of 0.8 is finally equal to 1. Now, if you take a few seconds to look at the result that we have achieved here, you will see that this is the logical AND function, not OR. This is the logical AND function. And so what our neural network does is that it simply computes the logical AND function. Nothing too magical. We're going to make a slight change to this. We have the exact same structure here, and we will have the same inputs A and B, and they will be binary inputs, and we will have our output Y, and we have A and B, and these are the possibilities when you have two binary numbers, the possible combinations. And what we'll do is, instead of having our weights as 0.4, 0.4, we shall have them as 0.6 and 0.7. And see what happens in this case. Now, this time, I would like to ask you to pause the video and try and fill in this table on your own. If you were able to fill in the table correctly, you will have seen that when A is 0 and B is 0, this summation here would be equal to 0, and Y is then going to be equal to, Y is then going to be equal to 0. When A is 0 and B is 1, this summation here is going to be 0.7, and Y is going to be equal to 1. When A is 1 and B is 0, the summation is going to be 0.6, and Y is going to be equal to 1. When A is 1 and B is 1, the summation is going to be 1.3, and the value of Y is going to be 1 again. Now, when you look at this here, what we have is the logical OR function. Now, if I zoom out and we look at these two results that we got, you will see that our first network right here is exactly the same as our second network. The structure of these two networks are exactly the same. The only difference is that the weights have been changed. And by changing only the weights of this network, we have changed it from computing the logical AND and made it compute the logical OR. The point I am trying to make here is that by only changing the parameters of this neural network, we have caused our neural network to learn how to compute the logical OR function. And for most machine learning models, this is how learning works. There are some numerical parameters that are changed, and by changing them, we essentially change what it is that the model computes. One more thing that I would like us to see, and this I would like us to see using some code, is here I've picked a new problem, and the problem is recognizing handwritten digits. And you will notice that this problem is significantly more complex than that of determining the logical AND and determining whether two inputs are similar or not. Now, in this case, I have picked 4 different models. The first has only 2 neurons. The second has 5 neurons. The third has 2 layers, one layer with 2 neurons, the second layer with 3 neurons. And the fourth has one layer with 20 neurons and another layer with 5 neurons. And when I train these and get their accuracy, what you will see is that as the number of neurons increases, the accuracy increases as well. And we can draw a graph to show this, but this we will do in a later unit. But the point we're seeing here is that as the number of neurons increases, the problem that we are able to learn also increases in complexity. This means that if you have a very complex problem, you need to throw more neurons at it. This is as much as we are going to look at today. In the next video, we will start actually creating models that do useful things.